This is a production of Cornell University.
All right, those of you who braved the elements out there, I mean vacation out there, why don't we get started? Are there any questions? We're gonna continue talking about colloids and less about the structure and more about the consequence today. But we're gonna just sort of get everybody back to par, where what we mean by this structure, and more importantly, the consequence of this structure. Because from our perspective, it's really cool. Don't get me wrong. I think it's totally cool, the crystalline structure, building. I mean, it's like puzzle pieces, putting things together. But some of you are like, no, it's not. It's terrible. No, but what's really, really cool about this is these structures and the natures of these structures really affect the charge of these structures. And when we start talking about nutrients later on, in fact, we're going to start talking about some of it today, it's these charges, these charged particles that are basically driving much of the nutrient behavior in the soils. If I have a charged particle, a magnet, the soil, colloid, in the soil, and then I put a charged ion in that happens to be a nutrient, okay, whether it's a positively or negatively charged ion, it's going to interact with that colloid. And that colloid potentially will hold that particle there, that ion there, for later use. In essence, this is the storage capacity. Think of this sort of as a bank. This is the storage capacity of soils to hold on to these nutrients, ions and cations, these nutrients that are in the soil solution. So they're not lost with the water as the system moves. Does that make sense? So today's lecture is really, okay, we're gonna touch base on what these colloids are, and we're going to talk again about what the nature of these colloids are. But what we're going to do is we're going to be moving into what's the consequence of this. And if we talk about these materials weathering and just we're fertilizing and we have stuff coming in from the atmosphere and we have decomposition going on, you certainly have an understanding that these ions are going into that solution, but what's happening to them in solution? Okay? So back to the colloids. We have 4 different types. We have the phyllosilicates. We have the non-crystalline or the amorphous silicates. We have the iron and aluminum oxides. And then we have the colloids, the organic molecules. Okay. All of these are charged. And all of them are charged at different rates and at different pHs, or at different intensities and at different pHs. Okay? These charges, there's basically 2 types. One is the constant charge and one is the pH-dependent or variable charge. The constant charge is associated with the structure. It's due to the nature of that structure. When we're talking about the phyllosilicates, we're looking at that isomorphic substitution, that charge imbalance that's part of that structure. And that's why we talked about how these things were put together, how they were built. Okay? We also have this variable or pH-dependent charge. This is both positive and negative. Generally, when we talk about isomorphic substitution, we generally think of this as a negative charge, but we can in fact have positive charge, but it is predominantly negative. pH dependent can be predominantly negative or predominantly positive depending upon what the pH is. Okay? It's primarily associated with those hydroxide molecules that are sticking out from the colloid that are sticking out into the soil solution. It's what's exposed, okay? And it is the primary source of charge on humic materials and iron and aluminum sesquioxides, as well as aliphanes and some of the phyllosilicates. Do you guys remember which phyllosilicate? It would be the phyllosilicate that has the hydroxide exposed. So all of them have the hydroxide exposed at the edges. But it's not until that octahedral sheet gets exposed when the tetrahedral sheets start weathering away that those oxygens are basically out into the soil solution. So in essence, the 1-to-1 phyllosilicates versus the 2-to-1 or the 2-to-1-to-1s. Does that make sense? I showed this picture before, but this basically shows you the different types of minerals. Okay, so we're looking at the less weathered minerals over here to the more weathered minerals over here. We're also looking at, in essence, more isomorphic substitution here than here. There's weathering, but as these things weather, much of that isomorphic substitution starts to disappear. The minerals become more pure. I don't really like that term, but does that make sense? Okay, and here you can see where the isomorphic substitution is, whether it's in the octahedral sheets or the tetrahedral sheets. Okay, and here you can literally see the charge that's associated with that single building block that's going to build up the larger sheets. Okay, so here's the charge. Okay, let's hold off on that. I showed this again just because I wanted you guys to see this sort of variability. Okay, so the variable of pH-dependent charge, that's due to this hydroxide that's sticking out, whether it's a part of an organic molecule, part of an oxide, or part of a phyllosilicate. And basically what we're looking at here, got white. Sorry about that. There should be a black line here. Okay, and right here you can see sort of where the white spots are there. Okay, there should be a black line here. Okay, as a negative charge, the negative charge that comes with this comes with increasing pH. So as I increase in the soil solution the hydroxide is going to be popping off that proton to make water. And as a result, I'm going to have more net negative charge associated with these hydroxides that are sticking out into the soil solution. And as a result, I'm going to get a more negative charge. Now, as the pH starts to drop, we start putting protons. See, there's the black line again. So we start seeing protons going into the soil solution. These protons are going to react with this hydroxide here, in essence making a water molecule and bringing a positive charge. So as the pHs drop, my charges become more positive. Now the consequence of this is that in this scenario, this colloid is going to be attracted to more positively charged ions because it has a negative charge. This is a negative magnet in essence. So cations, positively charged ions, are going to be attracted to it. So as the pH goes up, my soils can hold on to more positively charged ions. Things like calcium. As my pH is starting going down, I'm going to lose that negative and I'm going to start having a positive charged ion, positively charged attraction, which means my negatively charged ions are going to start to be attracted. My phosphates. Does that make sense? Okay. Questions so far? And I throw this, this is an older version of what's in your book, but I throw this in here so you can see this effective cation exchange capacity based on the pH. So as the pH goes up, my cation exchange capacity goes up for my pH-dependent charges. Question, go.
Going to the last slide again. Could you give an example of some more cations that, and where those might fall of different nutrients like calcium?
Oh, okay, so any of the positive charge. Okay, so the question was, can I give an example of more of these charged ions? Hold on to that question because, in fact, that's what the whole next part of this lecture is about. Okay? So what kind of ions would be a good representation of something that would be a negatively charged ion versus what would be a really good example of a positively charged ion that would be attracted to this negatively charged colloid? Question?
So in this picture right here, the solution is basic, and so then the molecule becomes acidic?
Yes, so the pH of the soil solution is increasing, so it's becoming more basic, okay? Because I'm increasing the concentrations of the hydroxide, which means I'm neutralizing the protons, okay? So as a result, this molecule wants more protons because it wants they want to balance these solutions, and so as a result, this proton's being pulled off the colloid at the edge and being turned into water. Actually, it's not. Okay, so the statement was the colloid is basically acting like an acid. And that's not really. It's actually acting more like a buffer. Okay, so it's buffering, and we haven't talked about buffers yet, but it's buffering the pH change by modifying the proton and hydroxide concentration, or mitigating it. Okay, so as I increase 1 protons, I'm going to have more hydroxides potentially in this, and that's so you see it's not really a hydroxide because it's not in solution. It's part of actually the colloid, but it acts like one, and the protons are basically attracted to it. So it's acting to buffer the proton concentration, the increase in proton concentration. Does that make sense? Go.
So does that mean that colloids don't have a pH level?
The colloids themselves don't. They do. There's basically 3 pools of acidity in a soil. Generally, when we measure acidity, we're measuring the acidity that's in the soil solution. But there's also an acidity that's associated with the colloids, and that's at the surfaces. And then there's a pH that's associated actually with the material itself. Okay? And it's called total acidity, but for all practical purposes, from a biological systems perspective, the active pool, which is the pool that's in solution, is actually what we really are measuring and what we're really concerned with. Now, in the long term, when we start talking about fertility management, we actually are also very concerned about this reserve acidity that's sitting on the colloids itself, because this proton, as the soil solution increases, this proton can buffer by changing that hydroxide and turning it into water. So in a sense, this proton can act to prevent the pH from rising. Okay, because if I start adding more and more of these into the soil solution, what should happen to my pH? My pH should start rising, right? But if I have protons here that can come off of my colloid and bind onto this and neutralize the hydroxide by turning it into water, it's in essence resisting that pH change. That term is called buffering. I'm buffering the reaction. Does that make sense? So in a sense, yes, these colloids are in fact acids and bases, but not in the sense that you're using. You're thinking of an acid as, a proton that's like a sulfuric acid. I put something on and it starts dissolving. Okay, does that make sense to everybody? Any questions on that? No? You feel good? Okay.
This has been a production of Cornell University, on the web at cornell.edu.